Hello everyone, good day. For our group's presentation, we are going to tackle about the Renaissance of mathematics. We are the second group and each of our members are assigned in different topics. So we have Mr. Badilla to discuss for the Italian Renaissance, artificial writing, the invention of printing and for Bombelli and imaginary roots of the cubic. Ms. Cabug-os for the founding of the great universities, a thirst for classical learning, and for the story of quintic equation. For Ms. Cajandab, she will be discussing the restoring of the algebraic tradition, the Italian algebraists, and Ferrari's solution of the quartic equation. And I am Ms. Camposano, and I will be discussing about CARDAN, a scoundrel mathematician, CARDAN's Ars Magna, as well as the story of quintic equation.
I am Jeffrey A. Badilla from the Group 2 of BSED 1B, and our discussion to the Italian Renaissance. If the 13th century can be seen as the highest point of medieval Europe, then perhaps the 14th century was the lowest. Although the 13th century had given abundant promise for the future, people in the 14th century saw the future as an endless succession of evils, despair, and defeat. Yet, the ultimate ruin which Western civilization was threatened never materialized. The calamities of war, plague, and famine had dropped off, with the result that population increased, compensating for the losses from 1,300 on, and the town began growing rapidly. Thus, after 2 centuries of chaos, political security returned with the abundance of the new monarchies of Louis XI in France in 1461, Ferdinand and Isabella in Spain in 1477, and Henry VII in England in 1485. The rise of this strong national state marked the demise of feudalism and provided the solid foundation on which a new European civilization, artificial writing, the invention of printing. The invention of printing revolutionizing the transmission and dissemination of ideas, thereby making newly acquired knowledge accessible to a large audience. Handwritten books were scarce and rare, and they need necessarily been the monopoly of the wealthy and scholars under their patronage. Those few books that were able to the public had to be chained down, and as further insurance against their loss. Many bore malediction damning anyone who stole multitude or even approached them without washing their hands. When it became possible to issue books not in single copies but in the hundreds or even thousands, the world of letters and learning was opened up to the moderately well-to-do classes everywhere.
I am Razen Cabug-os, discussing the founding of the great universities. The universities that were being established were to become prominent in the cultivation and spread of learning. The Latin universitas were originally a mere synonym for communitas, a general word indicating a collection of individuals loosely associated for communicating ideas. Initially, the only educational centers were monasteries. Their primary function was religious service, not intellectual, and they were designed to teach the outsiders. They preserved rather than added to literature. As the number of laymen seeking education grew, schools attached to the churches of bishops became prominent as centers of learning. Cathedral schools were provided mainly for those who would enter the ranks of the secular clergy and carry out on the work of the church in the world, not apart from it. Such schools are reached as a sideline to the work of the bishop and were prone to be affected by the reputation of the local teachers, waxing and waning with the comings and goings of particular personalities. Next is a thirst for classical learning. As the revival of commerce and the growth of town life in the 14th century gradually altered medieval culture, many efforts were made to shore it up or to replace it with something new. when neither the feudal nor the ecclesiastical tradition of the earlier period proved adequate. Intellectuals of the Italian city-states looked to a more remote past too and a congenial civilization. Most of the Latin authors, and as they later discovered, Greek authors had written for an urban, secular, and individualistic society not unlike their own. Italian scholars devoted themselves with a passionate zeal to the study of classical writings, interpreting them in the light of the present age. Behind this cult of the classics lay the belief that antiquity, both Latin and Greek, offered a model of a perfection by which to judge all civilizations, and in its literature could be found new solutions to all political, social, and ethical problems. There began a systematic and astonishingly successful search for a mislaid or forgotten manuscripts, many of which still existed in a few scattered copies.
I am Angela from Cajandab, and the assigned task that I will report is the Battle of the Scholar. Under it is the restoring of algebraic tradition by Robert Recorde. Recorde was educated at Oxford and then received the degree Doctor of Medicine in 1545 from Cambridge. He gave mathematics lessons privately in both university towns before setting up a medical practice in London. It is said that he was a physician to King Edward VI and to Queen Mary. Sometime around 1551, he was appointed to a position of surveyor of silver mines and monasteries in Ireland. Recorde's good fortune must have been temporary because he died in prison a few years later. The reason for his incarceration is not known, but it is most likely connected to his conduct in political of Recorde's Castle of Knowledge in 1556. It is a text on astronomy written as a dialogue between scholar and master. Is equally noteworthy for containing the RST discussion in England for the Copernican hypothesis of the Earth's motion. His position was guarded and non-committal, perhaps in fear of ridicule or worse, religious persecution. When the young scholar described Copernicus' ideas of vain fantasies, the master encounters, "You are too young, you were best to condemn no tinge that you do not well understand." Algebraics, who had under the weight of the cumbersome syncopated notation, began to introduce a symbolisms that would make algebraic writing more efficient and compact. One that was also better suited to the needs of typography. These improvements came intermittently, and there was a lack of uniformity in symbols, even for common arithmetic operations, or the present division sign was often used to indicate subtraction. Italian algebraics Paciole, Del Ferro, and Tartaglia. Italian mathematics in the 1500s can be summarized in the names of Del Ferro, Tartaglia, Cardan, Ferrari, and Bombele. The collective achievements of the first four was the solution of the cubic and biquadratic equations, and implicitly a deeper understanding of equation in general. Third degree or cubic equation were in no sense peculiar to the Renaissance. Attempts to their solution going back to the classical antiquity. We have seen that the problem of duplicating the cube, that so-called billion problem, attained social celebrity among the Greeks. These problems is nothing more than attempts to need two mean proportional between the length of the edge of the given cube and 2a, that is to solve a over x equal x over y equal y over 2a, which requires substantially the solution of the cubic equation x3 equal 2a3. Another noteworthy cubic equation is encountered in Diophantus Arithmetica in connection with problem 17 of book 6.
Cardan, a scoundrel mathematician. Girolamo Cardano, a Renaissance man, was born on 1501 in Pavia, Duchy of Milan, now Italy, and he died on 1576 in Rome. He was better known as Cardan, or in English as Jerome Cardan. Cardan was an Italian physician, mathematician, philosopher, astrologer, and a prolific writer. He was famed for his work on Ars Magna, which was the first Latin treatise devoted solely to algebra. In it, he gave the methods of solution of the cubic and quartic equations, which he learned from Tartaglia. His parents are Fazio Cardano, a lawyer in Milan, and his mother, Fazio Cardano was his father, and Chiara Micheria was his mother. Cardan's life was filled with tragedy and deplorable even by the standards of the times. He saw one son executed for wife poisoning. He personally cropped the ear of the second son who attempted the same offense, and he was imprisoned for heresy. Heresy means false faith or false belief, after having published the horoscope of Christ. Cardan's Ars Magna. Cardan wrote on a wide variety of subjects including mathematics, astrology, philosophy, music, and medicine. When he died, 131 of his works have been published and 111 existed in manuscript form, and he had claimed to have burned 170 others that were unsatisfactory. These ran the gamut from Practica Arithmeticae of 1539, a book on numerical calculation based largely on Pacioli's work of 1494, to Liber de Vita Propria of 1575, a book about his life in which he did not spare the most shameful revelations. His passion for games such as chess, dice, and cards inspired Cardan to write Liber de Ludo Alii, a book on games of chance. In permanent significance, his work, which is the Ars Magna, or the Great Art, or the Rules of Algebra, undoubtedly stands at the head of the entire body of Cardan's writing, mathematical or otherwise. The Ars Magna contains the techniques of arrangement of the cubic and quartic condition. It was first printed in 1545, that today would be classified as a text on algebraic equations.
The Bambili and imaginary roots of the cubic. Bambili was the RST mathematician bold enough to accept the existence of imaginary numbers, and hence to throw some light on the puzzle of irreducible cubic equation. A native of Bologna, he himself had not received any formal instruction in mathematics and did not teach at the university. He therefore decided to write a systematic treatment of algebra to be a successor to Cardan's Ars Magna. Bambili composed the RST draft of his treatise about 1560, but it remained in manuscript from until 1572, shortly before his death. Tremendously enthusiastic over the rediscovery of the Arithmetica, Bambili took 143 problems and their solutions from its RST4 books and embodied them in his algebra, interspersing them with his own contribution. Although Bambili did not distinguish among the problem he nonetheless acknowledged that he had borrowed freely from Dupiantos.
FERRARI'S solution of the quartic equation. The resolvent cubic after the cubic had been solved, it was only natural that mathematicians should attack the quartic or fourth-degree equation. The solution was discovered during work on a problem proposed to Cardan in 1540. Divide the number 10 into 3 proportional parts so that the product of the first and second parts is 6. If the numbers are called 6 over x, x, and x 3 over 6, the conditions laid down are clearly fulfilled. In particular, the requirements that 6 over x plus x 3 over 6 is equal to 10 is equivalent to the quartic x4 plus 6 x2 plus 36 is equal to 60x. After an unsuccessful attempt at solving the equation, Cardan turned it over to his disciple Ludovico Ferrari in 1522 to 1565. Ferrari, using the rules of solving cubic, eventually succeeded where his master had failed. At least, Cardan had the pleasure of incorporating the result of Ars Magna, with due credit given Ferrari.
The story of the quintic equations. Our story has a postscript. We have seen that in the case of quadratic, cubic, and quartic equations, explicit formulas for the roots were found that they were formed from the coefficients of the equation by using the four operations of arithmetic: the addition, multiplication, subtraction, and division, and by taking radicals of various sorts. The next natural step was to seek similar solutions of equations of higher degrees, the presumption being that an equation of degree n should be capable of formal solution by means of radicals and probably by radicals of an exponent not larger than n. For close to 300 years, algebraists wrestled with the general equation of fifth degree, the quintic equation, and made almost no progress. But these repeated failures at least had the effect of suggesting the possibility, startling at the time, that the quintic equation may not be solvable this way. The first is Paolo Ruffini, of 1765 to 1822. Paolo Ruffini was an Italian physician who taught mathematics as well as medicine at the University of Modena, concerned the suspicion of the impossibility of ending an algebraic solution for the general fifth-degree equation. Ruffini's proof, which appeared in his two-volume Theoria Generale delle Equazioni of 1799, was sound in general outline, although faulty in some details. The second is Niels Henrik Abel, of 1802 to 1829. Niels Henrik Abel, a Norwegian genius, when he was about 19 years old, he made a study of the same problem. At first, he thought he had found a solution of the general quintic by radicals, but later he established the unsolvability of the equation using a more rigorous argument than Ruffini's. The third is the development of Galois' theory. Galois himself was most significantly influenced by Lagrange. He criticized Abel and Ruffini more than he relied on them. Their results were introduced into Galois' theory by mathematicians such as Kronecker. Also, the early commentators of Galois' theory such as Cauchy, Betti, and Serret had no long-lasting influence on Galois' theory, due to a lack of original development in their commentaries. Mathematically, they can be seen as Abel's heirs, since they were interested in Galois' theory as a means to a computational end, namely the determination of the solution of an equation. The perception of Galois' theory changed considerably between the 1840s and 1930s. First, it was seen as a procedure for solving equations. Later, it was realized that Galois theory reveals a parallelism in the structure of fields and their automorphism groups. This change in the perception of Galois theory formed a significant part of evolution of algebra from the art of solving equations to the study of abstract structures.
And this is Group 2 from BSED 1B, Badilla Jeffrey A, Cabug-os Razen G, Cajandab Angel Love E, Camposano Nicole M. Thank you for listening and watching.